Good day, chemist in Japan de gozaimasu. Well, this is our THF, tetrahydrofuran still, and unfortunately, it's gone bad. THF is a solvent that we use quite often, so I'm going to replace it and show you how it's replaced. Alright, so in the first step here, this is the old steel pot. As you can see, it's black, and it's not good. So we use THF that needs to be absolutely dry, or as dry as possible. And so we take THF and we put it in this flask, and then we also put in potassium metal that will remove all the water. And then we add a compound called benzophenone, which reacts with the potassium to make a diketyl anion radical anion actually. And it turns the still blue. And it's a very pretty blue, you'll see it eventually, but when the still dies, it just dies like this, and it's horrible. And then we have to kill this because there may be potassium still left inside there. So we go through a very careful procedure of killing the still and making sure that there's no more potassium to react. So I'm going to remove that, and I have a temporary flask here in place. And this is the still head here, and there's its bubbler right there. So we're now going to replace this flask with a new flask, fill it with THF, put in the potassium, and start the still. So let's go get the new flask. So this is our new flask. This is actually a 3,000 milliliter flask, a 3-liter flask. We're going to be needing a lot of THF over the summer, so we're going to use this larger flask. The other one's a 2-liter flask, so this is a 3-liter flask. We'll get 1 more liter out of it, but it just allows us to do more synthesis before having to refill it and possibly, replace it. Because whenever you refill the still, there's a chance it's going to die. And so we're just going to use a larger volume, not much, but a little bit larger volume, so that we have more to work with over the summer. So right now, this was a hot flask. This came out of our 200 degrees C oven, and it's cooling down under a stream of argon. So it's cool now, so we're going to take this and we're going to put it over where the old flask was. So now it's time to fill the flask with the THF. So now it's filled, and we'll now cut the potassium. Alright, so here's our potassium. It's wonderful. It looks much nicer when it's cut. In a previous video I cut sodium, but I really like cutting potassium because it's so pretty. And this is mineral oil, where I'll place the pieces of the cut potassium. And this is hexanes, which is where I will remove the oil right before I drop them into the THF still. So I'm going to cut the potassium here. Now the amount of potassium that you put in is kind of just based on experience. This potassium is stored in mineral oil, and it cuts very much like sodium. It's very soft. Potassium actually melts at 63 degrees Celsius, which is why we use it in this still, because the boiling point of THF is 66 or 68, something like that. And the potassium melts, even though it is more reactive and could be considered more dangerous. But it does a much better job because it liquefies while the THF is boiling. Now, this is absolutely beautiful. Oh, it's oxidizing really fast, but it's just so pretty. So I'll cut this into really small pieces and kind of decide how much of it I want to use. Like I said, it's really an experience thing. It just oxidizes so fast, but it's that really pretty metallic color. Now what's going to happen, even though I'm cutting it into small pieces, once it gets into the still and starts to melt, they'll kind of form these large balls of molten potassium. And it's really pretty because once it's in the THF and it's boiling and it's all molten, there are these. It doesn't turn like a liquid and flow around like water does. It balls up, and it's really pretty because you have this large ball of potassium floating around with no oxidation, and it's just pretty. I think I'm going to stop with that right there. If it needs more later, we can always add more. But you don't want to add more than you need. Having a huge excess of potassium is very dangerous, especially when it comes to take time to take down the still. So that's the potassium in the mineral oil. And we're going to take this and we're going to drop these pieces. First I'm going to rinse them in hexanes, and then we're going to drop them into the still. And then after that we'll turn the still on and let it heat up, and it'll boil and reflux for some time. So we're going to go from here to here and into there. Alright, now that that's done, this is the variac. This is what controls the amount of energy that the heating mantle here gets. So this is a different heating mantle than the one that was here before, so I'll have to adjust the temperature until I adjust the setting until I find the correct setting to cause the liquid in here will heat up, and then it'll boil, and the vapor will come up inside the up this tube here, and then the tube continues inside there, and the vapor will reach these coils that have water and ethylene glycol mixture. It's at 0 degrees. It'll condense the vapor and it'll drip back down into this bottom part here and collect. I have the valve here open, so the liquid will just run straight back down into the flask below, but it goes through that cycle over and over and over again, and that's refluxing, and so that helps dry the solvent. And because we keep the solvent under argon atmosphere, the solvent will also degas as it goes through this process. So hopefully at the end we'll have nice pure THF that is free of water and hopefully oxygen. So now we're going to heat it and wait for it to boil. I'm going to estimate a setting of about 50. 40. We'll see what that gets us. Alright, we'll come back when it's boiling. It's starting to melt. Different pieces are deforming. Like right here. It's starting to open up right there. All the little balls of potassium starting to float around. They'll leave behind their crusting of oxides and corrosion from the air and water. They're floating around kind of individually now, but eventually they'll all kind of glob together. As you can see, the surface of the potassium is just absolutely beautiful and bright and shiny. Ball is running away. As you can see, these pieces over here have kind of conglomerated. Once it absorbs enough energy to really be a molten ball. And off they go. Unfortunately, all the crap will just kind of float around in there. It won't affect anything, affect the solvent as it's distilled and used. But unfortunately, it's in there and floats around. So as you can see, the balls are floating around, and they'll continue to do so and react with any water that it comes in contact with. And here the solvent is on its way up. You can kind of see it forming drops. And eventually it'll just keep going up into the collection part. But that's what molten potassium looks like. A big ball, silver ball. Now, for the rest of the day, we'll let this boil and reflux. And then tomorrow, we'll put in the benzophenone, and it'll turn nice, pretty blue. Blue, purple color. There they are, balls of molten potassium. Alright, we'll check it again tomorrow. Alright, well, good morning. So this is the second day. I let the still reflux overnight, and as you can see, there's still some potassium left. And it's turned this kind of brown color now because of all the reactions with the water and with the oxygen. So this is what happens to all the kind of crap that was there yesterday. It gets boiled and beat up, and it turns at this color. But now we're going to add the benzophenone, and you're going to see it's going to react with the potassium. That's basically what's going to happen is the potassium is going to react with the benzophenone to undergo a one-electron reduction. The potassium is going to transfer its electron to the benzophenone to create a radical anion, actually, and that will produce a very pretty color. So, but other than being pretty, it tells us that the solvent is water-free and oxygen-free. Although it's probably already oxygen-free because it's under an argon atmosphere, and because it's boiling, it's been degassing. But let's add it in and see what happens. Now the benzophenone must interact with the potassium for this to happen. So I put in 2 grams of benzophenone, which should be enough. So we will see. I may have to put in more, depending. Now, in the process of doing this, potassium is being consumed. But the beauty of using this indicator is that the keto radical anion that's formed from this reaction that's going on right now is that it will react with any water, oxygen, and peroxides. So hopefully, the benzophenone will act as a stabilizer to help prevent the formation of peroxide, which is always a problem when you're dealing with ethers. Ethers will react and form peroxides. Now typically, because of peroxide formation, I will take down a still fairly regularly just to be on the safe side, which is why it's important to use just enough potassium. It's always easier to add potassium rather than having to kill it off. because to kill it off, you have to react the potassium. You can't just take the potassium back out and assume it's okay. You actually have to, in a very careful and controlled way, you have to add different alcohols and react the remaining potassium slowly. So it's always easier to add potassium when it's needed than to have to deal with it at the end, because it is so dangerous. The same with benzophenone, actually. Other people, the books that tell you how to do this will often have you add an enormous amount of potassium, an enormous amount of sodium, of benzophenone. But this is so much easier to add just a little bit of potassium and a little bit of benzophenone. It's good to have the color, kind of the color that it is. It's this, nice blue color. But if you put too much benzophenone in, it's going to use up the potassium, for one, and two, it turns a very dark violet color. Where you can't even see inside, which can kind of sometimes be misleading to whether it's good or just dark, or whether it's good and dark or bad and black. So we tend to be sparing in our use of both, because it's going to continue to turn a really nice color. I believe one of the solvent companies, I can't remember which one, it's online, you can look it up if you really want to find out. They did a study on quantitative study on exactly how water-free the solvent is. And according to their study, a solvent dried and degassed in this method will only have about 10 parts per million water when it's done. But again, what's really nice is the potassium is molten and it's very easily seen. And it floats on the surface most of the time. So you know pretty much when you're out of sodium, because when you can't see it, then you're pretty much out of it. So this is the still. As you can see up here, it's a clear liquid that is collected. The benzophenone and everything stays behind as it's refluxed. So there we are. That's a solvent still, from beginning to end. Well, I actually didn't show you the end part. The end part's real dangerous. I'm not gonna show how we kill it off. Well, maybe I will. I don't know. Big ball of potassium. All right. Thanks for watching.